Hey Gary, I love this video because I've been trying to say there's plenty of non-phantasmagorical interpretations, and certainly you don't have to say anything about the particle making a decision. And also, yeah, you have to answer these questions if you are going to make this a more reasonable area. You know, if you just leave it so that it seems like magic, of course the magicians are going to come in. Now, Matt, to me, it's not appropriate to call it phantasmagorical. I mean, the phantasmagorical people are, you know, calling into Art Bell at night. I mean, as a phantasmagorical, you know, he's a very rationalist. He has a taste for the poetry of life, but you know, he's pretty rationalist about it. But anyway, that's another thing. Because just in general, you know, of course, if you leave it to you know, so that it looks like magic, you'll have people that like magic um, trumpeting it. Uh, the thing is, let's see. Okay, first of all, your idea. I like your idea. The you know coming up with theories of how space might be involved in this phenomena is very important. I mean, and is a part of quantum mechanics because it looks like in a vacuum you have quantum activity going on. You know, so it probably is something about the fabric of space time that'll play a role. But looking at your theory for your idea, I should say, for addressing the two-slit experiment, I think there's a couple problems. I mean, one, if these trails last, how long do they last? Forever? I mean, if they last forever, then you'd see the effects of all past photons flying through that space, even before the apparatus was put in place, right? Or um, since we're traveling through space, right? You'd you'd see, you know, all these trails being intersected. You'd see the interference pattern would change every time you did the experiment. Now, if the trails only last a little while, then how fast you fire individual photons would change the pattern. And as far as I know, it doesn't. You know, finally, as you said, we expect waves to be in a medium, and so they expected there to be a medium for light, the ether, and they found out there is no such single medium that all light is traveling through because you know even if there is an ether of some sort, it's a weird medium where it's always at rest to yourself. You know, if a water wave is traveling 100 miles an hour in the water and you fly over at 100 miles an hour or even you know underneath in a submarine, that wave will seem like it's at rest relative to you. That doesn't happen with light. With light, it always shoots away at the speed of light no matter how fast you're going. So there doesn't seem to be a traditional medium of any sort. Um, so I think that's a problem with that particular theory. But I you know I applaud coming up with this kind of thing and thinking about this sort of thing. In terms of having the extra slits, I'm going to have to look and see if they've done a two-slit experiment like that. Of course, they've done lots of weird things with two-slit experiments, including this quantum erasure stuff, which I'll get to in a second. But basically, I think what it looks like, and this is the part of the problem, is that even though it's not going to be like magic, it is going to be weird. It's going to be surreal, like a Dali painting or Picasso. Or there's a weird multidimensionality to what we have left in terms of options. We've eliminated the intuitive, classical, mechanistic explanation, so we're really left with explanations that are, um, you know, more surreal. But I think as we understand them better, they won't seem surreal. And just like, you know, it can seem surreal that the Earth's round. I mean, if I go in that direction long enough, I come back from that direction. Yeah, right. But, you know, it's not surreal now. We realize we're just a sphere in space. Makes perfect sense. I think probably we can achieve the same kind of understanding of this quantum stuff. But we will have to expand our mind to include, I think, relativity, for example, and a basic understanding of skepticism and these sorts of things which seem so weird to people. Um, so basically, we have this situation. We is our epitome of the two things that display wave and particle behavior. We have photons. They primarily display wave behavior. If you shoot them at the single slit, the pattern you see is what you would see by throwing a wavefront at the slit. The electron is primarily a particulate behavior, and if you shoot that at a single slit, you see the particle behavior. And the weird thing is that you can provoke both particle behavior from photons, which act mainly like waves, and you can provoke wave-like behavior from electrons, which act mainly as particles. Okay, so that's the weird thing. But the particulate nature of photons comes before this two-slit experiment, and tells us a lot about what kind of understandings we might have to have of reality, physical reality. Because now the idea of a wave, we'll use the metaphor of water waves because they're so familiar to people. It doesn't match perfectly because, for example, there's the medium of water, and we lack such a straightforward medium for light. And also, I mean, straightforward things like the speed of a water wave depends on its wavelength, whereas the speed of electromagnetic waves is constant regardless of the wavelength. But still, it's a picture for this model. We're applying models to reality. We're not expecting models to be perfect. We're just trying to get as good as possible. And we can certainly think of water waves and make adjustments so that the speed isn't dependent on those kinds of things, and make a pretty good model for electromagnetic radiation. Okay. Now in water, you drop a pebble in the water and a wave radiates out, right? There's no idea of that wave really being made of particles. A particle, if that wave is a particle, then what? There's a bunch of particles all in this ring that are going out? No. It's a ripple. In the case of electromagnetic radiation, what you can do is if you have like two electrodes and you jack the voltages right, and eventually the spark jumps. And when that spark jumps, that's like the pebble dropping in the water, and a ripple of electromagnetic radiation will go out at that time. So the weird thing is, though, there's a lot of ways to get the equivalent of these sparks to happen, and you can do it at a low enough energy that you get one photon at a time. Okay. It makes no sense in this water model, because that's like saying that as the wave is coming towards the beach, it's really a row of particles coming at the beach. Okay, so that means that there's like a slice of the wave. Head on to the wave. There's a slice of this wave that is just one particle that can be separated out. And it's not just conceptually that it can be separated out, because they're saying they can generate these waves so slow that we just have the slices come one at a time. Okay, so that's weird. Doesn't seem possible, right? A wave is this continuous, structure with a wavefront. It has an extra dimension. It's not just a little particle shooting. It's also got a second dimension here where it's the wavefront. All of these things of what would be multiple particles. So for a wave to be made of particles in that sense, it would only if the particles somehow all had to travel together. And they don't. They can be shot out one at a time. But what that looks like actually is that there's a multiple dimensional space. There's an extra space in which that single photon really is a ripple. And we're just seeing a cross-section. Because of the physics of our eyes, our physical properties of our eyes and senses, the baryonic matter we're made up with, we only see a cross-section. So the photon really does ripple out. We only see a cross-section. Okay. Now with electrons, you have a similar situation, but it's reversed because they seem primarily like particles. But if you do the two-slit thing, you can see what seems to be like when you fire that electron, that the particulate electron is just a cross-section of what's going on. What's really going on is, a ripple goes out of everywhere that we might see an electron, which is the cross-section. Okay. The reason it looks like that is because that makes sense. With two slits, if you have a wavefront, of course the wavefront comes up. It's got, it has length. It's bigger than the screen, and it comes up, hits the screen. Most of it's masked off. The part in the slits can ripple through and interact with itself. But whenever you provoke an interaction, when you put a detector in front of one of the slits, or for that matter, putting up the screen, the target where these particles hit, when you provoke an interaction, you're taking a cross-section. Okay, so it's the kind of a camera that can just take a cross-section. So like an MRI, when they scan someone with an MRI, it just takes a cross-section. Okay, we have eyes like that just take a cross-section for some reason. the whole thing is there. And then that's where quantum erasure comes in. The idea that they have really clever and very hard to understand experiments about quantum erasure